So when we are talking about structure of the molecule or compound, we want to know if the shape of the molecule, structure formula for the molecule. How does shape of the molecule is going to help us to study the molecule? Because shape of the molecule can help us with the understanding if the intermolecular forces. We can find out if the molecule is polar or is not polar. We learn about the functional group. The shape of the molecule. Do you remember from general chemistry what theory was used for determining shape of the molecules or formula units? Valence shell electron repulsion theory, or VSPR theory, helped us to determine if the molecule was tetrahedral, if it was like trigonal planar, if it was linear, based on the number of unpaired pair of unshared electrons, number of bonds. And then the other theory is hybridization. We also use the hybridization. For organic chemistry, since we are dealing with carbon, basically, as a central atom, we are using hybridization to determine the structure formula for a central atom, or the bond angle and all that for it. Since we're talking about hybridization, which is the combination of atomic orbital for one element, one atom. So we need to know about the behavior of the atom and the electrons, basically. So these are some of the electron configuration and all that, how overlap of atomic orbital is helping us to get the molecular bond or the molecular orbital for that. So when the bond forms is overlap of orbital between two atoms, orbitals of two atoms, but when the hybridization forms or hybrid orbital forms is the overlap of orbitals within the same atom, same molecule, or the same atom. So for example, yes.
Excuse me, I'm sorry. You have a student that got logged out and she's trying to get back in, but she's saying that she needs a link or something.
Announcement has the course ID.
Okay, so I'll let her know. Thank you.
Can you okay.
Her name is Justine Solomon.
If you could please help the student to get in from one login, that would be easiest way, but they have to just copy the meeting ID into the one login, or they go to D2L. It's easier from D2L. It's just one. It's from D2L is easier. So. Okay. So when the atomic orbital, they overlap, they form molecular orbitals. Addition of orbital is linear. What does it mean? It means that 1 + 1 is 2. If you have two atomic orbital, when they form bond, they would form two molecular orbitals. The two molecular orbitals, you have always seen this bonding orbital in general chemistry. That's the only concern that we have. The non-bonding or anti-bonding orbital is the orbital that we don't want electrons to be there. If electrons spend time in bonding orbital, the bond is strong. If electron is moved to anti-bonding, then the bond is going to make the bonds weak because they repel each other. They don't, is anti-bonding. It kind of pushes the nuclei away from each other. So the bonding orbital, when electrons move, these shared electrons is going to be attracted by two separate nucleus, the nucleus from each of the atoms, and it forms the bond. What happens when the bond forms? When the bond forms, which one is more stable? The atomic one, the ones that are square, or the molecular? Which one is more stable? The molecular one, right? When the molecule forms, actually the atoms that they form the molecule, they go from less stable to more stable, or from high energy to low energy state. If the atoms are going from high energy into the molecule, which are low energy, the difference in this energy is going to be released. This energy is known as bond formation energy. Bond formation energy. Now, if you have a bond and you want to break this bond, if you want to break that bond, then you have to spend energy. How much energy you have to spend is the numerical value in joules or calories is going to be the same as bond formation energy, but definition is different. The definition is going to be bond dissociation energy. So you have to spend energy to break the bond and send it to atomic level state. So you have two pieces now is going to be more unstable. They are going to have more energy, and when they have more energy, they are unstable. So it's an endothermic process. So when bond forms, energy is released. When bond is broken, energy is absorbed. Okay, perfect. The overlap of the bonds of the orbitals, we talked about the bonding and anti-bonding type of orbitals that these are molecular orbitals that would form as a result of overlap of atomic bonding. When they come in like phase in, this overlap is constructive and is going to give like a more stable. But since addition of orbital is linear addition, you get two orbitals. One is bonding and the other one is going to be anti-bonding. Overlap between s and p orbital can also form a sigma bond. So if this overlap is like a heads-on, that's what I start. This is like a sigma bond that you get here, and this is going to be a sigma star or anti-bonding orbital. And when you have these s and p orbital, they also can form a sigma bond. What is a pi bond? A pi bond is when you have two p orbitals that they are going to overlap side by side. So if they overlap side by side, then you are going to have the p orbital. Okay? So if you have a p orbital, you have a loop up, overlap of the electron cloud up and down. This is like half a pi up and half a pi down, and together is going to be like one pi bond. When the pi bond forms, you also have the pi, and then you have a pi star. And the pi star is the anti-bonding orbital that is forming. They exist, but they better to stay empty, because if you put electron in there, basically you are trying to push away the nuclei, or you're trying to break the bond. So electrons should not go to anti-bonding. If they go to anti-bonding or to non-bonding, they are not stable. Electrons, they like to be, when they form bond, the two atoms, they form bond and they form like molecular orbital. Electrons like to stay in the bonding orbital, which is more stable and is going to take less energy. The difference in energy is going to be released. Both pi bond and sigma bond releases energy when they form, but when sigma bond forms, which one is stronger? Can you tell me if the pi bond is stronger or the sigma bond? You can use the chat. I just want to make sure that you are participating and you're answering questions. Which one is a stronger bond?
Sigma.
Sigma is a stronger bond. The stronger the bond is, the more energy is going to be released, sorry. More energy is going to be released. So pi bond is weaker bond compared to sigma bond. So the energy that is released is going to be less. So we know the term of sigma and pi bond. What about single bond and double bond? So if we have single bond would be always sigma bond. Double bond is going to be 1 sigma and 1 pi bond. So if we have CC double bond, this is going to be 1 sigma and 1 pi bond. If you have CC single bond, is going to be 1 sigma bond. If you have a CC triple bond, it's going to be 1 sigma and 2 pi bonds. Now, which one is stronger? A double bond or single bond? A or B? Which one is stronger? Okay, between sigma and pi bond, sigma bond is stronger. But between A and B, because A is a double bond is going to be stronger than single bond because double bond is already composed of 1 sigma and 1 pi bond. And single bond is just a single bond. So there is additional coverage and additional overlap or additional sharing of electron that is happening for the double bond is going to make the double bond stronger than the single bond. When sigma bond or single bond forms, 2 electrons are shared. When double bond forms, 4 electrons are shared. And for triple bond, 6 electrons are shared. That's about single bond, double bond. The strength is going to increase from A, you have the B, A, and then C. So triple bond is going to be strongest. Single bond is going to be weakest among these 3, the double bond, triple bond. What about the bond length? Which one is going to be shorter? A, B, or C? Which one is shortest? Thank you for your response.
Is it B?
Shortest?
Is it B? I don't know.
Okay. Other responses?
Say C.
C would be shortest because what does it mean, strong bond? If it's a strong bond, that means that they are attracting the 2 nucleus, that they are as close as possible to each other, or they are closer to each other. And the weak bond, like you have a pi bond here, is very weak. Then you have like a sigma bond is strong, but if you have pi bond and sigma bond, is going to be even stronger attraction, or let's put it this way. It takes more energy to break the triple bond. So stronger the bond, also shorter the bond. What does bond do? Bond holds the 2 nucleus together. So if it's a stronger bond, the 2 nucleus is going to come closer to one another, right? So triple bond is going to be shortest, single bond is going to be longest. And the double bond, of course, is in
And the more bonds, the less energy in the molecule.
more bonds, less energy. I'm not sure. So more bonds, less energy. It could be correct. I just don't get the relation. So more is going to make it more stable.
It
Harder
requires
to
more
break.
energy to break it, but
Yes.
I don't know. Never mind. I think I was referring to a couple slides ago, but I'm not exactly sure what I'm referring to.
Okay, I can go back a couple of slides and tell me which one. Which
It was
one?
this one here.
This one?
The bonding molecular orbital the pi bonding.
For the pi
Yeah.
bonding. Okay.
Yeah.
For the pi bonding, it's like this, the pi bond is weaker than sigma bond.
Uh-huh.
So, but when you have, the pi bond doesn't exist by itself. So you have to have the sigma bond forming first, So if this is a sigma, the second one could be a pi bond, but the pi bond doesn't form until the sigma bond forms
Okay.
first. So the higher the order of the bond, the stronger the bond is going to be. And a strong bond means that holds the nucleus together stronger, is going to bring it together more closely, and is going to be shorter. Hybridization is a theory and is used to determine the bond angle for molecular compound, for organic compounds. It can it also helps with the shape of the molecule. The hybridization, it's a perfect example is for CH4. Beside the hybridization, or before learning about the hybridization in general chemistry, you learned about valence bond theory. In valence bond theory, it says that any orbital that is unpaired or is a single electron is going to overlap with another orbital from neighboring element to form bond, to pair up, to become more stable or share electrons to achieve the octet rule. So if carbon has only two orbital that is single bonded, singly occupied, okay, is allowed to make only two bonds. So if you have two p orbitals, one p orbital of carbon is going to bond with one hydrogen. So this is a hydrogen, this is a p from carbon, and this is a p from carbon. So another p orbital from carbon is going to form bond with another hydrogen. So you get two bonds allowed. That means carbon should form CH2 compound. Have you heard of this as a compound, CH2? It doesn't exist, right? CH2 doesn't exist. And since it doesn't exist, then they had to come up with explanation. How does CH4 then forms? Because carbon has only two orbital that has a single electron. So then the idea of hybridization came and said that, okay, if you have, if you excite this electron, if you give enough energy and you move that to empty p orbital of carbon, now you are going to make four of a singly occupied orbital. And that will allow the carbon to form four bonds. With the four bonds that is forming, now this is the s orbital, that's s orbital, these are p orbital, p orbital, and p orbital. You know the shape of s orbital and p orbital, they're different. We saw that in here. For the s orbital and p orbital, these shapes are different. Okay, the s orbital overlaps and p orbital overlaps. If p orbital overlaps, you get like longer bond length. With the s orbital, you get like shorter bond length. So the excitation itself, by itself, it didn't solve the problem, because the shape of the molecule, when they actually looked at the carbon with the methane, they found that these four bonds are exact same length for the hydrogen. So I said there must be another step. So this is a excitation. So we have the electron going to p orbital. We get four same like singly occupied orbital, but they have different energy. Now there should be like hybridization, like blending together, mixing the s orbital with p orbital. So they come up with like four new orbitals. And these four orbitals, they have more energy than s orbital, but less energy than p orbital. So, and this is called sp3 orbital. This sp3 orbital, that means that it's a combination of s orbital and p orbital. And the ratio of s to p orbital is a 1s for every 3p orbital. So you get four of these orbital, sp3, sp3, sp3. And so you get four orbital, and each one is singly occupied. Now, this carbon with four orbital that are singly occupied can form bond with 4 different hydrogen, and each hydrogen has 1 electron. And that solves the problem with the structure of methane, how carbon can form 4 bonds. 1 electron is excited to go to p orbital. Now you have 4 singly occupied orbital, and they can then form 4 separate bonds with the 4 separate hydrogen. So sp3, what you need to know, just that, what does sp3 means? sp3 is a hybrid orbital combination of 1s and 3p orbital. The shape is tetrahedral. The bond angle is 109.5. So that's what you need from sp3. Tetrahedral and bond angle 109. Now, with the sp2, okay, this is still talking about sp3. So sp3, these are showing the steps that we already talked about, the steps. There's excitation first, and then there would be hybridization. Then this doesn't work basically because they must be on the same level. It takes like 3 slides to explain the hybridization, and then coming up with the same energy level. So you get the hybrid orbital, which are the atomic orbital that overlap, and they form a hybrid orbital. It's just like a hybrid of, you could see that on for fruits and vegetable as well. So if you have like a tangerine and you have orange, when they hybrid, you get like tangelo. Tangelo is not half like a tangerine and the other half like orange. Tangelo has characteristic from both, but it has its own unique shape and a taste. So hybrid orbital, they come from the individual atomic orbital of the same atom from S and a P. And you would not expect to hybrid tangerine and orange and to get apple out of it, right? So it's something in between orange and tangerine. Same thing here, the orbital of S and P, when they combine, they give combination of S and P. So the hybrid orbital, it has some S character and some P character. It's not going to look like D orbitals. It's not going to look like F orbital. It's a combination of S and P orbital. So that's like the outcome. First of all, addition is going to be linear. So if you have 1 S and 3 p orbital combining, you would get 4 sp3 hybrid orbitals. And addition, the characteristic or the energy would be between the S and p orbital. Second, the condition when you are forming hybrid orbital, you have to combine the atomic orbital that they are close to one another in energy. Like after S comes P. You cannot combine S orbital with D orbital. You can combine S orbital with P orbital, and if you need more, you can bring D orbital, but you cannot combine S orbital with D orbital. So they must be close in energy as well in order to combine. So you get combination of the orbital. So this is a just summary of some of these, or demonstration for when you have an sp hybrid. This is the sp hybrid. For sp hybrid, the bond angle is 180. For this carbon has a sp hybrid. When it's the sp hybrid, you get like 2 hybrid orbital. 1 hybrid orbital of this carbon combines with the hybrid orbital from the other carbon, and then 1, it goes with the hydrogen. This is the sp2 hybrid. For sp2, you have the bond angle of 120, and then the shape is like a trigonal planar. The shape, when you have sp hybrid, is linear, bond angle 180, bond angle 120. When you have sp3 hybrid, bond angle is going to be 109.5. and the shape is tetrahedral. So that is kind of a summary. And then it does explain how each of these hybrid orbitals, these are review of what you have learned in general chemistry. And some of you might know already more than what is covered in here. Some of you is like, if it wasn't covered, if hybridization was not covered, then you're kind of depending on these. But the most of these are covered in the general chemistry course. What you need to know, if you have a compound, let's say if you have this compound here, C double bond C, and then you have a chlorine here, what is the hybridization for this carbon? Being able to find out what's the hybridization. The hybridization is going to be sp2, because if the carbon carries only one pi bond, is going to be sp2. If it carries 2 pi bonds, is going to be sp. If it carries no pi bond at all sigma bond is going to be sp3. So sp3 is 4 sigma bonds, sp2 1 pi bond, and sp is going to be 2 pi bond. That could be like 2 double bonds or 1 single bond and one triple bond. Okay. What is that alarm? End of the class time? Okay. So the next few slides is talking about the sp hybridization, sp2 and sp3 hybridization. Because it's the end of the class time, I'm going to stop the recording, stop here. This recording, when it becomes available, I will